Let's begin the lecture on vehicle dynamics and control with the first section on the kinematic bicycle model. Throughout this course, we will review some background material on dynamics and control, and we'll do this as we go along. And we'll start by a quick reminder of the terms kinematics and kinetics. Kinematics are about the geometric description of motions of point masses or rigid bodies in space, for instance based on different reference frames or coordinate systems. On the other hand, kinetics, or as they are more often called, dynamics, are about the laws behind the causes of motion. So, for instance, the acceleration of a body times its mass is equal to the forces acting on the body, which is a simple instance of Newton's laws. It is very important when dealing with any dynamical system to distinguish these two terms and also the notions behind them. So we will now start to look at vehicle kinematics, but of course we'll also look at vehicle kinetics later on. And we'll start by looking at the most important reference frames and coordinate systems that will be used in vehicle dynamics and control. From basic dynamics, we're all familiar with inertial reference frames, as those reference frames where Newton's laws apply, subject to the gravitational vector g. So in vehicle dynamics, the inertial frame is fixed to the Earth, and we choose the coordinates capital X, Y, and Z as the coordinates for the inertial frame. Here, the z-axis points in the vertical direction, anti-directional to the gravitational vector g, and the x and y-axis represent the horizontal plane, meaning that they are both perpendicular to the gravitational field. Next, the vehicle reference frame is a reference frame that's attached to the vehicle in what's called the vehicle reference point. The vehicle reference point can be, for instance, the center of gravity of the vehicle or the midpoint of the rear axle. The coordinates of the vehicle frame are called x with an index v, yv, and zv, and corresponding to the international standard ISO 885, they are selected such that xv points towards the front of the vehicle, yv points to the left side of the vehicle, and zv points to the top of the vehicle. And the vehicle frame along with the inertial frame are illustrated in the figure on the right hand side. Just like for the vehicle frame, also for the horizontal frame, the origin is fixed to the reference point of the vehicle. However, in contrast to the vehicle frame, the coordinates of the horizontal frame, which we will call by lowercase x, y, and z, have a different orientation. Namely, if we project the vehicle frame coordinates xv and yv onto the horizontal plane, then we get the x and y axis of the horizontal frame, and correspondingly the z-axis is perpendicular to the horizontal plane. So geometrically, what does this mean? Let's look at the little illustration on the right hand side, where the green plane depicts the horizontal plane, meaning it's perpendicular to the gravitational field. And what is drawn here is in red the vehicle reference point, and in white the coordinates of the vehicle frame. Now the x-axis and the y-axis of the horizontal frame are defined as the projection of the xv axis and the yv axis onto the horizontal plane. And then correspondingly the z-axis of the horizontal frame is the orthogonal vector to the horizontal plane. The fourth and final important reference frame is the path frame. The definition of the path frame is based on a path that must first of all be given. And then the origin of the path frame is assumed to follow this given path. For a better illustration, let's look at this graphically. So in blue here we have drawn the given path, and now we use one coordinate that we call S to define the location of the origin on the reference path. So for instance, suppose the origin is here. Now the coordinates of the path frame are defined as follows. The first axis of the coordinate system, which we call D, points in the direction tangential to the path. So for this we assume that the reference path is differentiable and D points along the path's direction. For the second direction, we first of all construct what's called the road plane. And the road plane is the plane that's tangential to the Earth's surface at the origin point. So this construction is based on the assumption that we drive on a flat differentiable surface, which could be a road, for instance. The second coordinate is called the e-axis, and it's defined as the axis that's perpendicular to the d-axis inside the road plane. And it's actually defined to point to the left of the d-axis. And finally, the third coordinate is called the n-axis, and it's defined as the direction perpendicular to the road plane, such that the coordinate system D, E, and N forms a right-handed Cartesian coordinate system. These four are really the most important coordinate systems that we will use throughout this vehicle dynamics and control course, and it's very important to have a good grasp of their geometric meaning and to be able to distinguish between them.